Look, we built 3 internets so far, okay? We built the fixed internet, connecting every single computer on planet Earth, and I think we have done a really good exercise with that. After we have done this, we started to build the mobile internet, which connects every single mobile phone on planet Earth. We went from 2G to 3G, 4G, and now we're in the room for 5G. And I think, again, we have done a phenomenal design. And after we have done the mobile internet, we moved on to the next internet, the things internet, connecting every single thing on planet Earth. And we're onto this. We haven't really concluded yet, but the connectivity technology is out there. And, about 4 years back, I was thinking, what's going to be the next internet? We've done fixed, we have done mobile, we have done things. What's the next thing? And the inspiration to this came at the height of the Ebola crisis. King's College London, my university, was leading UK's response in Sierra Leone. And our doctors were reporting back, we were lacking skills. We need people to help us down here in Sierra Leone. This is not about sophisticated stuff. We're not talking about doing operations. This is about palpation, taking temperature, giving some water, some food, a human being with a human being. And then I thought, hey, why don't we combine our best edge robotic skills we have on the planet with this emerging low latency network? And we throw a little bit of AI in there because it was already back then a very fashionable topic. And, we build an internet which actually would allow me to virtualize medical skills, literally bring in any doctor, any human being who can help into that crisis zone, okay? And I realized once something like this is up and running, I could literally do anything I want. I could teach people how to play the piano, which I happen to know. I can have people teach me how to paint because I'm very bad at it. Our best engineers could maintain engines. We could repair cars. We could do so many things if we are able to transmit touch and muscle movement, okay? And my hope really was to build an internet which eventually would democratize labor the very same way as the internet has democratized knowledge and information. And I gave it a name. I called it the Internet of Skills, okay? And people were laughing about me back then. And God is very quick these days. And what I want to do is, I want to take you on this journey of the last years, of this design journey, what we went through. And I would like to mention up front that Ericsson has been with me side by side from the very beginning, okay? They were the only ones who actually took me seriously from day one. And let's start with that journey. And, I thought it's going to be a fairly simple design because back then, we already talked Industry 4.0. So I was in France Telecom, Orange, and I'm the one who actually started Etsy M2M. So I wrote all the initial standards for the IoT ecosystem as you know it from an Etsy point of view. And, I thought it's going to be an easy ride. We call it Industry 4.0, right? You have seen slides on that, and you know that concept really well. But then suddenly I realized Industry 4.0 is not what I want to do for 2 reasons. The first reason is all we do here in Industry 4.0 is a local area network. It's an intranet we're building. It is important for the industries. We need it. There's no doubt about it. But we're building an intranet. The intranet has not worked for the internet philosophy. If you want to succeed, you need to build a technology which works from anywhere in the world to any other place in the world. It has to have true internet characteristics, right? I want to have doctors from London to go to Sydney, to Beijing, to Los Angeles, to Buenos Aires, anywhere to anywhere. That is what we want. Not an intranet, we want an internet, okay? So there's a big design change to the Industry 4.0 design paradigm. Then the other thing I realized is looking at this picture up here, there's a problem, okay? It's a solution for industries, but it's a problem for us because there's no human in there, right? So we're building technology which is empowering machines. I wanted something which empowers us. Humans, you're good in something. Do it, execute it, show your skills to people, use it remotely, etc. So I call this Human 4.0, okay, to give that a little bit of a counterbalance to this Industry 4.0. Call it Human 4.0. Think of it as you want. You may think of it like X-Men capabilities or X-Women capabilities, but it's really about building technology for the human being. And the inspiration to this came when I had a very long chat with a good buddy of mine, Hugh. So he's one of the most senior pilots in British Airways. And over a beer, because our kids go to school together, I asked him, hey, Hugh, you know, why do you still fly, actually? You know, I mean, we have the autopilot. The autopilot is doing things much better than you do as a human pilot. You know, if we had machines flying the airplanes, we would have had 10 times less accidents. We know this, okay? We know that. And he said, Mischa, you know, the only reason I get into this cockpit every morning is because if I didn't, nobody would fly, okay? Nobody would fly. Would you get into an airplane where you have no captain? Right? Here you go. Let me ask the different question then. If I had my Tesla parked out here, and I asked you now to go out, open the door, you sit inside, you turn around, okay? You start working, doing Netflix, whatever you do, whilst the car drives through the really crazy traffic of Milan, which I thought killed me 5 times yesterday. Okay? Not crazy, okay. I know, you have a different league in the south of Italy. Ecco. Okay. So, honestly, who would do it? Who would do it? You see? Right? So we all talk in autonomous driving, we talk whatever we want to talk, and we as engineers in the room, we understand it's 10 times better, it's 10 times more efficient, 10 times more reliable. The brain understands, the heart doesn't, okay? So this is when I realized that, you know, it is very important to design a technology which has the human in there, okay? It's not only about machines, it's not only about automation. It is really important to have it in. So that's why I started that whole design journey, right? And we went off the road, and I actually sat down and I thought, you know, how do we do this now? How do we do this now? And, you know, the internet took 40 years to jail. It took a long time. You use it today, you think it's been around just almost immediately. It took 40 years of design engineering of some of the best brains in the world. I don't have that time. I want to do it quicker. So I looked at the concepts, what's made the internet succeed. And that's the top row you see there. So as we transited, you know, we started with an ecosystem, you know, 40, 50 years ago, which had comms capabilities. If you're lucky, you had a video phone, a Siemens video phone. They existed back then, right? And you could use it. You could talk with somebody else on these video phones, but the requirement was that that person also had a Siemens video phone. And they were really expensive, okay? And the circuits weren't even, the network wasn't even circuit switched. It was human switched, yeah? You remember those days? You probably remember. I wouldn't remember that, but, you know, you had these plugs going in. So, and then we did magic. 40 years, we designed a network, we invented IP. So as long as a machine speaks the IP language, they can talk to this new infrastructure. And we invented something else, which you may take for granted, but was absolutely instrumental, and these are the codecs. Right? The video codecs. Today I can take a video on my iPhone and I can play it on my Dell computer. With that, we locked out the verticals, we brought down the cost, we scaled the network, and the rest is history, as they say. That was really important. These two things were absolutely instrumental. And we're starting with the same thing today. Is it possible today to transmit touch in muscle movement? Yes, you can do it. I have that machine in King's College London, that thing here. Da Vinci robot. So we have a doctor sitting in the viewing portal, looking inside, doesn't even see the patient, which is lying on the table behind, and manipulating with his hands, her hands, the actual operation. We can do it today. But here's the problem. The cable which connects these two devices is proprietary. Okay? I cannot break it up. The other problem is that thing costs £2 million. Okay? Now, for Europe, it's a little bit cheaper now after Brexit coming, but never mind. We cannot build an internet of skills. We want something which is super cheap, consumer grade. That's what we want, okay? So I sat down and said, we need to do things. Network, codecs, okay? Network, we need to do something which works extraordinarily quick. In fact, it has to work within 10 milliseconds from any point in the world to any other point in the world for two reasons. The first reason is a lot of our human interactions happen within 10 milliseconds because the time it takes from the optical signal to reach my vortex is 10 milliseconds, okay? So therefore, I have that feeling of immediacy, of being with you right now, right here, because the signal comes within 10 milliseconds. If you do a Skype call, you don't have that feeling because it's more than 10 milliseconds. If we get it down to 10 milliseconds, we can have, over this future Skype, this feeling we are together in a room together, okay? So that's one of the reasons. The other reasons is more from the mechanical side, stability reasons, control loops. So if you do some action and reaction, this has to be felt within 10 milliseconds. Otherwise, your systems become unstable and you do start doing things which you don't want to do, okay? So 10 milliseconds was a little bit of a challenge, which if you break down the system, the air interface has to be about a millisecond because you have more things in between. But you do the math very quickly, we'll come to this. So network needs to be done, next generation network, and that's why in the room, 5G is a big enabler of that. And then the other thing is the codec. I will not talk about the codec today, but so I started a new standards group where we are standardizing touch, where we standardize kinesthetic movement. We don't have it, right? So what we're doing is essentially building an MP3 for touch and for movement. So what I really want to avoid is that in the future, you will have an inner skills device, an exoskeleton, which works only with ABB, or Siemens, right? We want to break it down. That's what we're doing at the moment. So let's move on to the network, and let's understand a little bit the challenge. And challenge number one is the delay. So if you look at this, I've shown you the length of this chart here is the delay, the latency, and one of these boxes is 10 milliseconds. We have to do everything within 10 milliseconds because that's what my human vortex reacts to, okay? So that's a challenge. So I work a lot with London, Los Angeles. So you see the delay here. You will know this, okay? So we have 36 millisecond speed of light, about 40 millisecond speed of light. We do have a network which gives us congestion and delays and the buffers and all that. So, and I experience about 40% of all the delay in the metropolitan area of London, and the other 40% in the metropolitan area in Los Angeles. Once I'm on the fiber highways between the Atlantic, I'm good. Okay, so that's more or less under control. But really, the metropolitan areas is a problem. And then you have application delays. People forget about it. You know, you can design a microsecond interface as much as you want. If your video codec takes 60, 70 milliseconds to actually encode and decode the signal, there's no use of doing these very ultra-low latency systems. No use. Okay? So therefore, we have that delay. It's a huge, in fact, I cut it because the screen isn't big enough. So this delay is gigantic. Now, how do we bring this down to 10 milliseconds? How do we build an internet where I can actually do what I want to do from any point in the world to any other point in the world? How do I do it? Well, this is probably a talk of another 5 hours, but let me be very quick on that. So the first thing we do is, well, hello, you know what? We don't compress. Let's get rid of compression. So if you don't have video compression anymore, you have no delay. Okay, you could argue that you could buy a very expensive video compressor, so there are some devices which can do video compression much quicker, but again, it defies the point of an internet, a consumer product. Okay, so I want to work really on something which is a consumer product, so we're not compressing, we're actually just doing a very light compression. Okay, so you get this down to 0. The other part, the yellow one, is you do slicing. You're very familiar with that, so the magic here, though, is end-to-end. It's less about slicing, it's about the end-to-end. There's no use if British Telecom does the slice in the UK and then Verizon doesn't do the slice in the United States. Is no use to me. So it needs to be an end-to-end slicing ecosystem where all the operators on the edges, all the tier 1, 2, and 3 providers, fiber providers, have a sliced architecture end-to-end. Okay, so that's really, really important. Otherwise, we can't get rid of these yellow boxes. Okay, and finally, to beat the speed of light, which is probably the biggest challenge, we have borrowed a concept from the gaming industry. Okay, so when you play an online game today and it's a world cloud game, you are on your phone or on your device and you're doing some shooting, whatever, right? So that control signal goes to a nearby edge, and in fact, this cloud where the rendering is done has no time to wait from the player in Sydney to take a decision. So what they do is they predict. They know the player. They know how the player reacts, okay? They know what the player typically does because we are animals of repetition. So they're predicting the player's behavior in Sydney, weave it into the game engine, they render the image and stream it down to you, and you have a feeling as if it's actually instantaneous, even though the control signal from Sydney comes in often 60, 70 milliseconds later. Okay, so that's what we borrowed, and it works really well. We can stabilize systems to about 100 milliseconds today, which I think is a great technology. So here we are. We are able to get it down, in theory, to 0 milliseconds. In reality, we are about 20 to 10 milliseconds today, which is good enough to have an internet running across the planet with ultra-low latency. You also understand we cannot do everything with that. Okay, there are limits to this. But as long as you pose the questions to human engineers, they will find the solution, right? So, and I'll give you another example later on. Now, your delay problem, the solution to the delay problem by not compressing gives you another challenge, and that's the bandwidth challenge, okay? You understand that very quickly. So if I have, what I'm showing here is the bandwidth versus the encoding horizon. So today, I have quite a good horizon. I have enough time, 100 milliseconds compression. A true VR comes about at a gigabit per second. So the stuff you see in the hall, in the demo room of Ericsson down there, okay? It's about a gigabit per second true VR. If you don't have time to encode anymore, that's going to be 10 gig per second. All the video traffic, once you stop compressing, is about an order of magnitude above. Okay? And I see a lot of appetite for real-time stuff. What does it mean? All the Cisco predictions for network traffic in 2025 multiplied by 10. Okay? Multiplied by 10. And I mean it. Okay? So you cannot tell in 2025 that nobody told you. I told you. Remember that day, 24th of October 2018, with just 1% of the world's traffic being real-time traffic, all your dimensioning predictions, all your investment stories is just off the chart by an order of magnitude. Please bear that in mind. That relates to transport network, resource schedules, to the spectrum availability, the rollout, etc., etc. Okay, so bear that in mind. It's a big tsunami coming because of what I just told you. And therefore, your bandwidth problem really translates into a headache for the operators, really, and that's an architecture challenge. The true challenge is an architecture challenge. So what we did is, as a community, we tried to understand where did all this wireless capacity come from over the last years. And there's a chap called Martin Cooper who allegedly did the very first wireless call in the United States. And he said capacity has increased over the last 35 years by a factor of 1 million, approximately, right, over the wireless interface, a factor of 1 million. Now, we sat down and we started to dissect this. Who played which role there? And we figured out that a new physical layer, so as we move from 2G, 3G, 4G, 5G, is a factor of 5. Spectrum, so for all the regulators and government people in the room, is a factor of 25. And fasten your seatbelts, ladies and gentlemen, because the actual big capacity increase came because we made the cells smaller. Now, the operators in the room, you guys know this, okay? So I'm preaching to the converted here. But the real challenge is how do we really build the architecture? Where do you put your antennas? How do you front wall them? How do you backhaul them? Where do you put your cloud RAN? How do you do your functional split? These are all questions which will become super burning in a 5G system, because that will become yet another headache. Does it make sense what I'm saying? Yeah, so my delay translates to, my exciting application of an Internet of Scales translates to a delay challenge, translates to a bandwidth challenge, translates to an architecture challenge. So it's a tough thing to take. What I thought to do is now skip about 200 slides, because I just thought I'll show you what we did, okay, together with Ericsson. So we have a 5G system up and running as of December last year. The first non-standalone standard was just frozen. We then have optimized, and we worked very, very closely with Ericsson, and I'm very grateful for this. Probably we're one of the closest collaborators, because we even developed APIs together, etc. So what we have here is, on the left-hand side, you see the actual physical deployment. So when you come to King's College London, in fact, I'll show you a video later on, you will see that. You will see 3GPP compliant 5G antennas. That is a massive MIMO antenna, 3.5 gigahertz, 8x8, cross-polarized, so 64 multiplied by 228 RF channels coming out. They're all front-hauled down into the baseband unit, which is right here. Do I have a laser here? No. It's right here. Okay, so the antennas are there, and they're front-hauled into the baseband unit. Interestingly, the baseband unit is the only kind of purpose-made unit in the whole infrastructure. That's a big transformation. Eric talked about this. We're talking about softwareization of the ecosystem, okay? So it is the only purpose-made. It's FPGA. There's a powerful FPGA in there because the stuff which needs to be demodulated and decoded is just so bandwidth hungry that you need to do it. The rest runs on, configured purpose-made hardware, so the cost is much cheaper. But of course, the magic now is in the software. So where it goes in next is the RAN, virtualized RAN, access network, virtualized core network, connects to our infrastructure. We run Wi-Fi, 3G, 4G, 2G, IoT on top as well. And then we build an orchestrator on top, which currently speaks OSM and on up for the tech geeks in the room. So fully cloudified, fully virtualized, fully flexible in a sense. That's what we have. So I'll take you on this journey now, and you can see it firsthand. So I'm in front of the Bush House here, King's College London. We acquired that from the BBC for a lot of money because universities lately are more about real estate business than education. Never mind. So I'm walking through the entrance hall here. So you're most welcome to visit me at any time, walking in there. I'm going now up with the lift to the 8th floor. Where our coffee shop is, where I have my coffee every morning in London. And again, you're most welcome. Well, look at this. That's the roof of London. Okay, so we're literally overseeing the London landscape. The church you see here. Now you get a better picture of that one. There's a church here. This one here. So Hans Zimmer recorded the theme for Interstellar on the organ there. You see the big band there is currently a London Eye. For some reason, London only has one eye. Never mind. So we have right here the antenna, the massive MIMO antenna, the squared one on the adjacent building. You barely see it. So what we're doing is now we're going into the courtyard where they're pointing towards. You see the squared one, massive MIMO, just beside is a millimeter wave, 28 gigahertz on both ends. They're front-hauled down into our 5G bunker where we have essentially all the virtualized servers and the BBUs down there. Okay. So this is up there. You can connect to this. We work with a lot of operators. We provide a kind of a neutral platform to do that. Okay, right, so we also do a lot of policy work. I know quite a few government people in the room, so I'm on the advisory board of Ofcom, which is our regulator. A lot of, the thinking around spectrum needs to be changed within 5G. I'm happy to share that offline. You're most welcome to download our policy paper we did. Probably my biggest contribution is the evidence I gave to the National Infrastructure Commission in the UK, where I forced them to rethink public street furniture. I had to put up 3 antennas on my roof, and it took me 6 months, and I thought I was not able to do it in the end, okay? I don't want to know what you guys go through rolling out hundreds of thousands of antennas in the country on rooftops and lampposts, which are not yours, okay? So I told this to the NIC. I showed them this green capacity graph. I said, we need to rethink how public street furniture is being handled at national level. Again, offline discussions, just want to let you know that we have done this homework. Let's go on to the really interesting thing. And that's a question, what do we do with that? Okay, what do we do with 5G? So I know that a lot of the demand-side people are in the room, people who will be using the technology. And I started very early, 2014, probably one of the first ones to ask the questions, if 5G comes out in 2020, what can we do? I wanted to avoid the mistake we did with the Internet of Things world, so I have a company in IoT, and we struggled at the beginning with the demand side. We knew the IoT had a need, so it would be great to have. But is there anybody paying for that? Okay, is there a name, surname person paying for that? This is what defines demand, and there was not, okay? So I wanted to avoid this. So I started to reach out to verticals, 2014 onwards. We spent time together, co-creation, co-design. We spent not only PowerPoints, this was sitting day in, day out, weeks, months, and years until they got it. There is, every single vertical told me, I don't have time, I'm not interested, and I was insisting. We got the stuff off the ground, and every single vertical said, this is awesome. I want 5G tomorrow. So I managed to sway them from perceiving telecoms as a cost factor in their bill to something where they see value. Okay? And this is where you want your customers. Okay? Because when they see value, cost is not an issue anymore. When they see it's disrupting their business model, they're okay to pay. Okay? So, and that is exactly what we achieved. Let me take you through some of them, very small subset. One interesting thing we did is with Ericsson, Verizon, and BT, we had this big drone industrial drone in the courtyard at King's, and we had a guy controlling it. And what we did not tell the guy is that the signal wasn't controlling the drone directly. This time the signal went all across the Atlantic and came back. It was this fully end-to-end sliced architecture, okay? And he didn't realize. He didn't realize. So what we wanted to prove really is that in this future 5G world, you could have industry-controlled, very critical processes run from any point in the world to any other point in the world. You remember my sentence about the internet? That's exactly what we wanted to do, okay? So what else did we do? A little bit on the challenges here. So this is a little intersect, a bit of a funny one. So I told my students what I told you before, that it's not possible to do everything through the Internet of Skills, and particularly I could not imagine having a tennis game, something quick through the Internet of Skills. So 2 weeks later, I come back to the lab, and this is what I find, okay? So they built this prototype with a tennis rack attached. There are two students which are not in the video. One of them built a Wii kind of device, which was doing the actual hits, while it was connected to the sliced architecture to the Atlantic, going to Verizon all the way back into the UK. And the other one was throwing the badminton, okay? And they're doing well. Right? So you can actually play a tennis game through the internet. I'm not sure what the use of that is. Maybe Rafael Nadal could teach some kids how to play. But you know, I mean, you can do it. So I'm saying I post them. I told them it's not possible, and they just did it. All right, so, and that's the beauty of the human mind. So that's what we did. What else did we do? We worked a lot of medicine. Maybe you've seen it, but I would like this video still to be played. If you could put up the sound, please.
We need to disrupt the way we
This is
see
a
medical
doctor
treatment.
talking.
If you see an
Doctor.
open surgeon operating, they will have a bit of tremor at the ends of their scalpel. The robotic instruments are computerized, so they have absolutely no tremor. There is one problem though. There is no sense of touch at the end of the instruments. It is very difficult to transmit across remote distances and across current robotic systems. In order to do this with haptic feedback technology, you need two things. You need network slicing and you need cloud data sharing. I think both are possible through 5G. It also allows us to bring the best education internationally to the next generation of doctors. It gives us the opportunity to educate anyone, anywhere. Often we have to go to their hospitals, to their sites, to mentor them.
So I'm cutting this video, it's on Ericsson's site. A doctor speaking, network slicing, edge cloud technology. It's phenomenal, right? I mean, can you talk about, I don't know, vortexes or about arteries and veins and sinews? Yeah, this is how far we got it. So this is Prokar, Professor Prokar Dasgupta. He's a pioneer in robotic surgery. Okay, he's one of the first ones who have introduced it. He happens to be at King's College in London. We have 4 hospitals. So the conversation was easy, and he's a great guy. I mean, you know, if you want him for a keynote, I'm sure he would come. He gave me a few homeworks. Give me back the feeling of touch. We did. Allow me to have the operation across at least London. I live in London, North London. I have to operate in South London. I don't want to commute an hour and a half one way every day. We can do it. Sliced architecture, okay? And the other thing is we allowed him to do now is to teach people at scale, because he can record the way he does the operation, how he cuts, how he sews, etc. We can record it. We have the haptic technology to do that today, and we're building what I call this standardized skills database where we would store the skill of Prokar. We do the same with dentistry, because you need to know how to do dentistry, and doing the same with the piano, etc. So the idea is to play this back onto exoskeletons until people get the muscle memory to do exactly the way how the best people in the world do it. And then we can do exams. We can even do exams on the physical and touch thing. Nobody could do that before. Exams were on paper, right? Now we can do it with the... So that's one of the things we're driving at the moment towards that Internet of Skills. What else did we do? A really interesting project we're doing currently with Ericsson and China Mobile in China. It's about colonoscopy. So it turns out colon cancer detection rate in rural China is very bad. So a lot of people die because it has not been detected early enough. It's not a problem of China. You know, it just happens to be that good doctors, they have good doctors like every nation, but they want to be in the capitals. They want to be in Beijing, Shanghai, and Guangzhou, and nobody wants to live in the rural areas. We have the problem in the UK, in India, in the United States. So what we thought then is to do exactly the Internet of Skills. Hey, you know what? Build a very cheap outlet in the rural areas, and for this I called my buddies from the Robotics Center who built a fully soft robot, so there's no metal part in there, fully soft, ultra-low latency connected into the best hospitals in China, and then you would have the best skill set, do the right diagnosis at the right time. Okay, and we hope to save a lot of lives with that, and this is just taken off. What else do we do? With Ericsson again in St. Petersburg, fascinating project. So this is the Hermitage, and in one of the most premier arts venues, and there's a really famous restaurateur in there. And we told him, look, imagine you could restore art across long distances, you know? And it's particularly pertinent to, you know, war-torn crisis areas like Iraq, Syria, where you really want to maintain some of the world heritage, but you can't fly there. So he was very resistant, and then we came along and we built him this Internet of Skills trial, full immersion with VR, full control with ultra-low latency, full immediacy, and he loved it. Okay, he loved it, and he thinks that has a real application in that world. What else did we do? So a bit on the art side, a bit closer now to my heart. Not this guy, but the guy before you've seen is Peter Gold. So this guy, Peter Gold is #2 DJ in the world, and he was DJing in Avalon in a big club in Los Angeles. And we had him connected into an adjacent club off West Hollywood, and he was hologrammed on there on the pyramid, and the crowd was dancing there. Now, you don't need 5G for that. But what we did then as well is we brought an image of the crowd back to Peter in real time, because we wanted him to adapt the BPMs of his music to 2 dancing crowds, okay? And there you need 5G because you need to actually close that loop, because with 20, 30, 40 milliseconds, not good enough. So we got this up and running, and suddenly, I realized, what we're doing is actually something much more than, this virtual reality, augmented reality world, because we're bringing realities together. Right? That's what we do. So we coined this term synchronized reality, which I think will be the next big thing underpowered by this ultra-low latency internet, right? Synchronized reality, bringing environments together. So that's what we're doing. We're currently preparing for a global DJ event. I'm working with Chemical Brothers and Massive Attack on that. So the idea is to have a club. When you go clubbing, I'm not sure you know, but when you go clubbing, you go in a club, 12 o'clock, good music, nobody dances, okay? And what we want to do is really bring in the atmosphere of a club which is already 2 hours dancing in a different time zone, in real time in there with holograms and all that, so we actually get people really warmed up and dancing, right? So that's what we want to do. And so the idea is to start somewhere, Sydney, then we go Tokyo, Beijing, Delhi, Moscow. We're going to have Berlin, Ibiza, you know what, maybe Milan, yeah, okay, got it. We have London, we go off to Reykjavik, and then we do Miami, New York, and then we do San Francisco and LA, and then we go to Honolulu, and we do the whole thing again, okay? So that's the idea, to do that, and I'm sure that will work really nicely with this internet. Okay, last slide. Along the same lines, let me just make this music play for a second, and then I'll explain you what happened there. Do you know the song? Yeah? All right, so this is Kiss, okay? Kiss, the band. And they did a song called I Was Made for Loving You. And then Maria Mena did a cover on that one, and we did a cover on the cover, okay? So that's a double cover song. And so I was in Berlin under the Brandenburger Tor playing the piano, and we're lucky enough to have this young lady in, so she's a child performer in the Royal Opera House. Conveniently, she's also my daughter, I have to say, so that is, and her dream is dream number 2, actually, I just came back from Sydney where I did a gig with Ericsson down there. Her dream number 2 is to sing in the Sydney Opera. And when I told her I'm flying to Sydney, she got really upset. And you know what her dream number 1 is? You can guess. To sing the Milan Opera. Yeah. And when I told her I'm flying to Milan, she stopped talking to me. So if you can make it happen, I can at least speak again to my daughter, right? So right, so what happened here? Guildhall. She was singing in the Guildhall. The Guildhall is the UK's oldest entertainment venue. the Romans introduced it 2,000 years back, okay? And we thought, hey, let's marry a very old historic venue with the newest technology called 5G. She was saying from there, the end-to-end latency was 20 milliseconds. Now digest this. I'm not sure it really means anything to you, but if you use your computer, this computer there, which is currently displaying that, takes about 35 to 40 milliseconds to get the signal only out of the sound card. And we had 20 milliseconds delay latency between Berlin and London. 2 different geographies, 2 different countries. I could feel her singing speed. I was adapting in real time to her singing speed. She was adapting to the pitch of the piano in real time because we could only practice at home, and my piano at home has a different pitch, right? And it was so emotional to have my daughter there on the other side of the channel, 1,000 kilometers from me. So I really struggled not to cry during the actual performance. It was just beautiful. Anyway, so we are there. We can do it today. This is the future public internet. We can do magic over this future public internet. We use new codecs, and you can see a wonderful demonstration of Ericsson down there called Music Connect. And it's all leading to these wonderful applications which 5G will bring. So thank you so much for your attention.